Okay, let's go ahead and get started. Basically 2 minutes late. I think that gives us time to let interested people come back in. So I'm Gary Carleton. I was here on Monday talking about prototyping parallel code, prototyping the changes from a serial program to make it parallel. What I'm going to talk today about is a little more detail on one of the technologies that we've integrated into that tool I described Monday. This is the Intel Inspector that looks for threading errors and memory errors. So this is a more focused tool at that particular individual, or those two individual problems, relative to sort of the broader prototyping mechanism I described before. Now, we had a few questions in the intervening time relative to measuring certain kinds of performance metrics on our processors, cache misses, branch mispredictions. That's something that I actually work on in my real job. So I think I'm going to try to find a way to maybe get a little more information back to the PARLAB community. I don't know if I add a slide to the presentation with some comments there, but we've got a fair amount of material that describes exactly how to measure, how to use some of our tools, or actually anybody's tools, to measure those performance attributes that might be causing programs to slow down. We've got basically an algorithm, I guess it's more of a process, with numerical milestones that can indicate whether there are too many cache misses being generated in a program. It's affecting performance, and some ideas on what you can do to reduce them. So I'll try to see if I can get some of that content to be integrated into the material that we post relative to this conference. Today's topic is the Intel Inspector. This is a second generation tool. We had a tool some years ago called the thread checker that basically was the same kind of concept. The idea was, let's look for data races and deadlocks inside a program, or at least the conditions that may allow them to occur. Detect them, flag them to the user, and allow the user to make changes to the code to reduce or eliminate the possibility of these particular kinds of errors occurring. So I'll talk today about the specific tool that we have in terms of the first two bullets in the agenda. The third one, I'll talk a little bit more about how it works, some of the, to be honest, some of the issues with the technology. And then I think the fourth topic is really the new one here. I put these slides in this very morning. About, I'd say 4 or 5 years ago, we had one of our researchers lead a team to use these tools to thread a large application. So I'd like to discuss some of the good things and the bad things that resulted from that study. And then a few sort of miscellaneous topics at the end, a little more on the practical side of using this technology. So the Intel Inspector is a tool that we actually market. It's available from Intel, licensed in a number of different ways. There are academic licenses, there are commercial licenses, evaluation licenses. But fundamentally, it's a tool that runs on Linux and Windows to provide the capability of identifying the potential for data races to occur and to do some memory checking across thread boundaries and across processor core boundaries. So that's essentially what it is. We're trying to identify memory leaks, look for incorrect API usage, or maybe not matching the allocate and deallocate APIs correctly. But I think perhaps more significantly, and we'll get into this, threading issues. Again, the case where we're looking for the possibility that data races may occur, and the same for deadlocks. On my presentation Monday, I had a question, I don't think he's here today, but I had a question on were there command line capabilities? Was there a command line version of the tool? So I inserted a bullet right up front to indicate that yes, this tool, there's a GUI-based version of it on Linux and Windows, and there's also a command line version on Linux and Windows. So either way, and we have users, we have customers using them in both manners. So they're there, and they can actually interact. You can gather performance data with the command line tool, import it into the GUI, and have the full GUI analysis with drill down to source code. Okay, so key features. Again, memory and threading analysis is what this does. And I wanted to at least start with the idea that this is dynamic. It doesn't look at source code. You actually build the program and then run the binary. And our tools will trap certain events that occur as the binary is executing, gather the data at the time of the running, and then do the analysis after all the data is gathered. So this is not a real-time kind of tool. You don't see results as you're going through it, as you're running the program. But we do this in a kind of a post-mortem analysis. I mentioned we have the GUI on Windows. Actually, I'm a little curious. I'm not really sure how to break this up in terms of Windows or Linux. How many people are programming or interested in Windows environments? Okay. How many in Linux? That's what I guessed. Okay. Actually, there was more Windows than I expected, to be honest. Okay, so we do both. We do both environments with this tool. In terms of Windows, we do, as I mentioned on Monday, our tools can be plugins to Microsoft's Visual Studio versions. So that is available. But we also have standalone GUI versions for both Linux and Windows. Languages for this C, C++, C#, and Fortran. I think we had a Fortran question or two from Monday, if I remember right. Was that you? Asked about Fortran? Yeah, okay. So I made sure that I had the answer to the question on the slide here today. Okay, so I'd like to kind of show you a quick look at what the features are from the perspective of the GUI of the tool. Actually, the way the rest of this presentation will go is I'll go through the technology and some screenshots to try to help you understand exactly what this is all about. Then I want to spend time on that case study where we attempted to parallelize the Intel compiler. And then if there's time, I'd like to do a little demonstration like I did on Monday to just kind of show you how the tool really acts and what it can do in a more interactive manner. But in terms of what we're doing now, I wanted to point out that this is the screen where you're determining exactly what kind of measurement you want to make, what kind of performance data do you want to gather, or correctness data, actually, you want to gather. With both of the modes that we have, checking for memory errors and checking for threading errors, you can identify the amount of, or sort of you can indicate the level of intrusiveness you're willing to tolerate based on the amount of detailed data that you get back. As I mentioned, both of these technologies work on the binary as it runs, and we trap certain events as things happen. So there's a certain amount of runtime overhead that occurs when this analysis, actually when the data gathering is occurring. So you have the ability to select exactly what level of information you want to see, which will relate to how much runtime overhead you're going to experience when the program runs. Let's see, I guess I probably should talk about some of the other things that are in red here. Up at the top, that represents the set of icons that get installed if you use this as a plug-in to Visual Studio. If you're using just the standalone GUI, again, those are the icons that you'll see. And actually, this is the standalone GUI. Not sure we can tell whether this is, yeah, this is on Windows. But it looks virtually the same on Linux. Off to the right, we have the major controls for this. Once you've set up the type of analysis you want to occur, and if there are any overriding of the default settings, you'll just click on Start, and that begins the program or begins the analysis, depending on how you've configured it. And it will run until it finishes, again, depending on how you've configured the finish event. And then down at the bottom are two features that we've really changed in this second generation of the tool. Our previous tools kind of had configuration parameters scattered across a bunch of different windows, depending on exactly what mode of analysis you were looking at. So the project properties, the goal of project properties is to put all the overriding properties or settings in one place so that you can go there and just change whatever it is you want to change. You know, this binary, give the application to run a command line interface, use this as the starting directory. Lots of different things that you can configure with project properties. In addition, a piece of feedback that we got from the first generation of tools that I think I got tired of hearing actually after a while was that the command line version of the tool, the syntax for it was kind of sensitive, shall we say, to order of parameters and things like that. So we added a feature where you can go into the GUI, configure a performance test, and instead of clicking start, you can just click on show command line, and it will give you the syntax, the command line syntax for that test, and you can then copy and paste that to a script and use the command line version to get the same performance data. In terms of the results that come back, in this case for memory problems, but the overall format is pretty much the same for both modes. We give a list of problems. For a selected problem, we'll give a list of the specific event occurrences that cause that problem. So for example, if there's some kind of memory issue where the malloc and free don't match in some manner, that's two events. Both of those will be indicated here, but up in the problem description, there'll be a alloc and deallocate mismatch. So the idea is to indicate individual problems. The component actions that cause that problem are down here. And then off to the right, which we'll talk about more with the case study, you have the ability to filter the data. In real applications, you don't necessarily have one or two or three problems. You can have hundreds of messages coming out. So we felt very early on with this tool that there needed to be the ability to have the human user focus on certain classes of problems, or at least to try to organize the set of problems in some manner that made sense to the user. So we have a number of filters that you can apply to all this data to really, again, focus your development efforts on those problems that are most significant. I guess a little bit of history. Actually, this is another good question here. Has anybody ever used any Intel software development tools? VTune, compiler? Okay, yeah, got a few brave hands.
I have a small question.
Sure.
What does XE stand for?
Yeah, that's a question for our marketing and branding people. Let me think if I can remember. See, I'll get trouble if I invent something here.
That's
you know, in a public environment, someone's going to go to some lawyer and get me fired. So, I'll give you, as an individual perhaps, and not as an Intel employee, we actually have two different versions of this tool. There's the Intel Inspector without the suffix, and then Intel Inspector XE. XE is the one that has more features and more capability and more configurability. So I think in some manner XE may stand for expert. But you know, I didn't say that. Yeah. Yeah, extra features. But you didn't hear me say that, okay? Okay, so we've had a set of tools that we've had in the past. The thread checker was one of them. This is a tool that actually I think came from one of our corporate acquisitions. You may be familiar with Cook & Associates in Champaign-Urbana. I think this technology came from them. But in any event, this is a tool that we've had. Again, it was a standalone tool. Didn't exactly support all operating systems in a similar manner. So we've taken that tool, improved it in a number of ways. The instrumentation technology is different now in the inspector than it was in the thread checker. We have a more unified user interface format versus all the other tools in addition. But fundamentally, we started with the Intel thread checker and produced that there. There was, I didn't even know this had an actual name, but we had a memory analysis tool that I think never went public. At least I'm not familiar that it did. I see what this is. This is inspector without the XE. Okay.
Yeah, and I saw there was also an inspector with an XE.
Yeah. So the one without is has less functionality and is actually Windows only also. XE is Windows and Linux. But again, I would still assert that the XE in some manner is supposed to stand for expert in some marketing person's eyes. Okay, so we took the memory analysis work that had been done over the last 10 years and integrated that into Intel Inspector also. Something I'm perhaps not going to talk a great deal about, but probably should mention just for the sake of completeness, is that if you actually get the full Intel Inspector XE package, there is a static analysis, static security analysis capability that comes along with that. We've basically taken the Intel compiler and we can scan through the sources and list a few thousand different types of errors that can statically be detected by a compiler just doing that one pass. So, if there are obvious buffer overruns where we can see, the for loops that scan through are clear enough that the compiler can figure out what's going on at compile time, there'll be that kinds of things. But there is this mode just for the sake of that. So it's really sort of these three technologies merging together with a unified GUI, I think is what this is about. Okay, so let's look at the product in a little more detail. In terms of the usage model, when is it that you use it relative to the rest of the development cycle? Essentially, choose target means you indicate what executable program it is that you want to do the analysis upon. So you choose a target. If you want, you can configure details about how the data gathering phase will occur. If necessary, you can rebuild the program because this tool is going to want to see line number and function symbols. So you may have to go in and turn on symbol generation to get that. You then run our tool to get the analysis data. Then once the data is generated, you can focus on a set or an individual problem that comes up in the GUI. Look down and see where in the code are the events causing the problem. Make some changes and go back and see if you fix the problem. This is fundamentally the process. I think we've pretty much talked about most of this. I guess could just mention that in the analysis phase, you can also see call stacks. So if you have a particular place where there's some kind of data race occurring and you want to look at the source code for it, you can actually see what the most common calling sequences were into that particular function that caused the issue. So the stack frame depth is there, and you can adjust that to increase or decrease the overhead at runtime as you see fit. So select analysis type, click Start. So a little clearer look at the results that can come out. So in this case, we've found one data race. The data race occurs as a function of 4 different events that are happening. And we have the enviable situation where there's really only one error occurring throughout the binary. But the key point I want to make here is that for a particular error that pops up, when you want to get into more detail about what's going on and how to fix the problem, you can double click on this item here. So that's the number one there. But the idea is you can double click on that item and it'll then show the sources for the different events that are causing the problem to occur. So in this case we have a data race. Looks like it's based on accessing global X, where we might have different critical sections based on this variable occurring. I guess at this point it might be good to talk about how this actually works. I think I didn't put in many slides about the technology behind this. What we're trying to do here is solve the classic problem of a data race that generates bad results every once in a while, intermittently. Any of you that have done any amount of parallel programming have faced this nightmare. You know, a lot of bugs are really nice. They occur all the time. They're repeatable. You bring up the debugger, you know, it still fails in the same way, and you go there. The problem with data races are they tend to be timing dependent. So, you know, you might, with one run at one point, the error pops up, but the timing may be such that most of the time the error doesn't happen and everything goes along. You just get the failure every once in a while, and it's not repeatable. And oftentimes when you connect a debugger to the utility and try to take a look at what's going on there, the debugger itself causes the problem to not occur, just based on different timings and different things happening. So we wanted to have a technology that would not wait for the data race to produce bad results. We wanted a technology that would indicate to the user that there's a potential for a data race to occur. So the way this works is actually fairly simple. We look at global memory references, trap them across different threads, and when each thread, or let's say when a thread references a global memory data item, we look to see what synchronization objects are being held at the time of the reference. So we'll look and see what kind of locks or critical sections or mutexes are being held at that time. And then we let the program continue to run. Another thread comes along, references the same address. We capture the list of locks that are being held by the other thread. This is all the program does as the program's running. This is all our tool does in the data gathering phase. Shared resources accessed, a global memory address is referenced, which locks are being held at the time of the reference, and then just go on. So what we do is, once all this data has been gathered and the program's completed, we then go back, sort it by the memory references, and look to make sure that the intersection of locks being held by the different threads is not null, that there's at least one synchronization object that all the threads were holding when there was a reference to that variable. So we're essentially looking to make sure that the synchronization is correct, that there is the ability for the references to be safe. So every time we see that this does not happen, we'll give a data race error condition. Again, as an indication to the user that we think there's a potential for a data race to happen. Don't know if it happens or not, but we're seeing synchronization that's not proper for these two or more references to the global variable. We have a number of ways you can modify this information. We have a number of customers that don't necessarily use, pthread locks or Win32 locks. They have their own user synchronization mechanisms. So you can go in, and once a particular data race happens, you can mark it. Actually, you can right-click and give it a state. You can say suppressed. I don't want to see this message again, or maybe I want to see it, but just line it out. I know that it's okay, even though the tool thinks that it's an error. So you can indicate suppressed. You can indicate fixed in case it is fixed, perhaps in another build of the program, but in this version it's currently not. The idea is to allow for, perhaps not special cases, but for customization of synchronization mechanisms that different customers will use. So what we're trying to do, I guess what I'm trying to say is we're trying to reduce false positives as much as is reasonable. You know, we detect all the conditions. We allow the user to go in and say, that's not really a problem. Let's just keep going. So navigate to the sources. That call stack appears off to the right for each of those two sources in this case. There's also a timeline that will indicate in this particular run at what point in time these different events occurred. I guess I'm not necessarily, I guess everybody's got their opinions about things, but you know, I'm not so convinced that seeing a timeline in this kind of mode is a good thing, because I think it might start to convince people that you know, the timing relationship is not going to allow the data race to happen. Okay, so that's kind of a quick walkthrough of what's going on. Next, we'll talk a little bit more about the details of how it works, and I think I may have talked about most of this. So, data-driven, you know, what we see is the execution based on the data you apply to the program. This is not a static analysis. We're actually, the program runs and we're watching the program as it runs. So the behavior of your program may be a function of the data. Program can be single or multi-threaded. We'll still do the analysis. The diagnostics do become reported. So this view here is populated as the program runs, but the analysis of drilling down to the source code is an after-the-fact kind of a thing. Okay, so in terms of memory analysis, again, the kinds of things that we watch: memory allocation and deallocation, memory leaks, memory API usage. These are the types of things we're watching. And again, we're watching this across multiple cores. So it's not, I think most of the memory checkers that we see out there now are sort of more serial kinds of tools. We wanted this to be scalable up to any number of cores that are out there. Threading analysis is also dynamic. You run the program to get the results. And the way it's actually done, like I said, we're watching thread and sync APIs that are used so that we know what objects are being held by the program at different times. And we do this for .NET. This is not something we did initially in the first release, but it's there now. Does anybody care about .NET? Is it something I should spend time on? I don't know if 2 constitutes a quorum. But I guess enough said that these features, at least the threading analysis, in terms of watching for data races and deadlocks, occur with .NET also. Okay, so it's, you know, nice that we have this technology. It's actually pretty exciting. Maybe I don't sound excited enough. I had kind of a long drive this morning. But the question that almost always comes up, and sometimes audiences are too polite to ask the question, is, you know, it works. So this tool seems to have worked pretty well on, you know, this little data races.exe. Doesn't really sound like it's necessarily a real program. Sounds like it's some special case test program or something. So the question always comes up: how does this work on an actual production large program? And so one of our researchers, maybe 4 or 5 years ago, felt that was a question that needed to be answered. So we took the Intel compiler, which was serial at the time, and decided to try to parallelize it using this tool and a few other tools, but I'll focus on just the steps involved in using this tool. This was it was an interesting project. It occurred sort of across multiple time zones, actually. But again, the idea was to take a big serial program and use actually that predecessor for the Intel Inspector XE use the Intel thread checker to see whether we could reasonably thread a program of this magnitude. So it's 1,000 C files, millions of lines of code, and we essentially used the version of the Intel Inspector that existed at that time, 5 years ago. So just a word on the participants. Mo Hagigat was the project leader for this. He came from University of Illinois at Champaign-Urbana, compiler guy. Actually worked on the compiler at Intel for a while before moving over to Intel Research. So he did this. There were a number of compiler engineers that participated in terms of the nuts and bolts of making a lot of the changes. But Mo was the one that really focused on the process and trying to identify what needed to be done. If you're interested in the details, the paper is published at that location. Okay, so he felt that the process to be followed, and this is actually fairly similar to the Intel Advisor that I talked about on Monday, and this is not a coincidence. The Intel Advisor, the idea of that as a tool, to a certain degree, came from this project. So, discover parallelism. Try to find which portions of the program are the best candidates for parallelism. Express the parallelism. In the case here, actually write some code that makes it parallel. In the case of Advisor, you do some macros that quickly get you a look at parallelism. But in this case, they decided to parallelize it in sort of a simple model as possible. So OpenMP was selected for that. Then debug it. What kind of data races were generated by moving this large serial program to parallel, and do some tuning of it. So I'm going to focus this effort on the debugging stage where we're looking for issues in the threading model for the purposes of the next 20 minutes here. Okay, so the way the compiler is structured, is similar to every other compiler. There's a driver program that looks at a subroutine or a function at a time and simply compiles it, does some analysis, does multiple phases of optimizations. Finally at the end, so with intermediate code, finally at the end, the actual assembly language code, machine code, gets generated. So this is the initial version of the compiler. This needed to be serialized. So in terms of trying to identify what portions of the program should be parallelized, they did an analysis similar to what I did on Monday, where they tried to find those portions of the program that were using the most CPU time and focus their attention on that. Okay, they decided that the way to parallelize it is to simply take that whole process and try to enable the ability to compile separate routines in parallel. Now, they encountered many issues with this, as you might imagine. There's symbol table references that need to be updated and referenced across these boundaries. The intermediate language can often be dependent between these. Various optimizations can cause transitions in more than one function, inlining or partial inlining, for example. So this was the model that they faced, but they were pretty concerned about data races, data dependencies, and how much synchronization they were going to have to put in. They decided to use OpenMP as just a simple, perhaps naive, but at least a simple way of getting parallelism into the program. And then they ran the thread checker on it. So thread checker in projection mode. Projection mode, the paper that I cited before, it talks about that. Or actually, this paper here talks about it a little bit more. But the idea is that you don't necessarily have to be running all the threads independently. Projection mode can take a serial program and project how that's going to operate in a threaded environment, is essentially it. So they ran the application looking for data races. The technology that thread checker uses, and actually Intel Inspector uses, I briefly mentioned that this idea of which synchronization locks are being held by in each different thread when memory references occur. So it talks about that there. But they ended up with Thread Checker, Intel Inspector essentially, reporting 300,000 data race errors. And so I took a look at this and didn't know what to do next. It's such a big number that you really can't proceed. So they needed to try to organize all of these in some manner. Try to find the ones that they believed that many of these messages were redundant, but how do they know? They needed to, again, try to organize and filter this set of errors into something that was more manageable. Let's see, I guess I didn't talk about that anymore, but that led to this idea of filters. I probably should have talked about that more before. Off to the right, there was this, when we saw the GUI, there was this set of filter items off that could indicate which type of errors you wanted to highlight, which source files you wanted to highlight, which functions you wanted to highlight. Maybe I can quickly. Yeah, so that effort, when things were just too out of control, led to this capability of filtering all the data into a smaller subset that's more relevant to what you're doing right away. So they essentially started with those filters and spent the next few months trying to make 300,000 be smaller. That's really the goal. So Mo kept a log as he went through this of how many errors were being reported after each build. And his point, which is going to sound obvious, but perhaps wasn't so much at the time, was to identify those specific source code transformations you could make that would affect the largest number of these messages. So he would try to focus on certain portions of the program where there seemed to be the most data races or those type of errors occurring, and just went through that summer trying to reduce the number. And occasionally, he actually came out with a way where he could show regressions where problems would come back after he had reduced them. So that's part of the real world also. So I guess we'll say over from July to September, August, over 2 to 3 months, he managed to get it down to at least 2 digits worth of issues. The goal was to prioritize those error messages or violations and fix the ones that would result in the highest count. When he started with 300,000, you couldn't just do 2 a day, for forever. There had to be a nonlinear way to do it. So this is what they ended up doing. This is for the first half of the project, and then the second half here. One of the issues that came up was, when you have 300,000 errors, the GUI that we had at that time, without the filter capability that we have, was really not useful in his opinion. So he had to, actually the group had to do a lot of sort of customizing the analysis with their own tools in certain ways. But again, this led to changes in our product as it exists today. And the final speedups that we see, or that he saw, are referenced by this. There's some of the SpecMark programs are down here. Looks like some floating point, some integer. The legend on the right indicates the number of executing threads and as to whether the load of those threads were balanced or unbalanced. So you just throw some threads out there. You don't really make any effort to balance them versus trying to define the workloads so that we have a more balanced functionality. But essentially, as you can see, we're seeing sort of around a 3x improvement on a 16-way system, about 2.5 on an 8-way. So the conclusion the group's conclusion, complex applications can be parallelized. You have to understand the difficulty you're going to have. You have to be able to use the tool in an efficient manner to try to focus the issues that you're going to look at. The tools seem to work. Managing the size. I talked to Mo last week, and he kind of has the feeling that maybe 300,000 messages is still a challenge with the tools as they exist today. But it was a doable thing. Okay, readying your sources and builds. So what do you have to do to get this tool to work with your program? We use instrumentation technology called PIN. It's a sort of a instrument as you need it, just-in-time instrumentation, perhaps. Oh, it says that there. Capability for both the synchronization APIs and the memory accesses. The thing to realize is that this technology, this Intel Inspector, is going to increase execution time and memory consumed. So the bigness that you mentioned before is something to consider. So it's our recommendation that you try to downsize the program as much as possible, not by changing the code, but perhaps by presenting smaller data sets to it. In the case of the compiler, if you're going to be compiling programs, use relatively smaller programs to compile. The goal is to try to execute over as many different instruction code paths as possible. As long as we can get to a code path, we can do analysis of it. So that's a key point here. Okay, I think this pretty much is just ideas on, again, trying to keep the amount of execution time to a reasonable minimum. And specifics in terms of building. With this tool, we're recommending you actually generate a debug build, not a fully optimized build. That gives us more sensible line number symbol attribution to the execution addresses that we see is really the reason. Doing this kind of thing to optimize code is, I guess probably most of us know, the line numbers that you often get with optimized code are pretty much a compromise based on the kind of optimizations that an aggressive compiler can produce. So generate symbol information, disable optimizations, and then that would produce the build that should work best. So recommended analysis sequence in terms of these three states: security analysis, the static analysis first to see if there's things that you can easily fix. Check for memory errors, check for threading errors, and hopefully you'll have a more stable program as a result. Okay, child program analysis. We've faced this with a number of our tools, is that the program of interest is not necessarily the one that you just start right at the start. There can be scripts or other programs that fork other processes, kind of a thing. So we do support this model where the actual program of interest is generated or is created by some other entity in the system, not directly by our tool invoking that particular program. As I mentioned, we have a command line interface for this. So you can essentially you can collect performance data, you can collect threading and memory error data from a command line, from a script. We have a few customers, maybe it's more than a few, I guess I don't really know, but we have customers that use this kind of as a last step of a new build. So when a new version of the program is being built overnight, typically, they'll throw in some command line invocation of our tools to collect information in an automated manner, and then the programmer can subsequently take a look at that information and see if anything new has popped up. Can also generate reports generate analysis reports based on the command line. We have, I guess I mentioned on Monday, there's a server company I visited recently last week that has a large number of servers, but most of them are not ones that people program into. They're server farm kind of non-GUI systems, so they don't have GUIs. So they use this command line version of the tools, actually not just this tool, but other tools, to gather performance data from these non-GUI systems and then import them into the GUI on a development machine. And they can look at the analysis of the data there. So you don't need the GUI to do data collection. But you can still get the full analysis capability of the GUI from command line generated data. And a couple of papers to look at. Let's go ahead and take a look at this in a more interactive manner. Okay, so Monday, I used the Intel Advisor to take a look at this program that was using Huffman encoding to compress a file and then expand it back out and make sure it was okay. And we found, looks like I didn't go back to the original version of the program after I left here. But in any event, we had this program. That was serial. We threw in a couple of macros, and it told us that we could speed things up a little bit. If we implemented parallelism in the manner described by the macros, and did a few other things relative to task chunking and I forget what else, reducing amount of overhead. But this was essentially the code here. So in the meantime, we have taken this and parallelized it, then run it. So that same program where we've actually used the threading building blocks, the threading library we produce at Intel. The idea was to thread the program, run it, and see if we have any problems as a result of the newly created parallel version of the program. And it turns out a number of data races were detected. So let's see. I guess that particular place, there's data races in other areas here, but that particular file that we went in and modified, or I went in and modified, we had frequencies.h was the serial version, made another one, parallel frequencies.h, that had the threaded building blocks parallelism references in it. And sure enough, it's showing that we had some data races created by some reads and writes occurring as the program ran across different threads. So if I double click, I guess before I double click on it, here's that filtering that I mentioned. So if we look at just that source file, for example, we can see the errors that were created by any reference to that particular file. So this is essentially what we did in the parallelizing the compiler, is only looking at certain categories of messages that came back out. So we actually had 6 data races. Okay, so I've not gone in and suppressed anything. So here's where I can go in and indicate that a particular item has been fixed, or essentially trust me it's been fixed, or it's not a problem because I've got my own synchronization mechanism. There's not a data race. We're just not using the normal OS-based APIs to do it. And we can suppress individual events. Perhaps we know from the timing of the program that it's impossible for, let me go back to a more sensible issue. We may know from the timing of the program that it's impossible for these events to occur in a manner that they're happening at the same time, essentially. So We could indicate that by suppressing the event. And there's more kinds of things we can do there. But in any event, if we want to look at more information on this, we can double click on it and navigate to the source code, as with a lot of our tools. And we'll essentially see that section of code. Let's go back to the serial version, where we have this for loop, and we're building the STL map inside of there. We have this tool telling us that that's a data race, that we can't, this is not a thread-safe operation, and there's no synchronization occurring around this. There were not synchronization objects being held, at least not the same synchronization objects being held when these two different threads executed this statement. So we have a potential data race here that needs to be dealt with. Okay, we got a few minutes left here. That's pretty much it for the normal content here. Any questions at all on any aspect of this or any tools, any Intel tools at all? Performance questions are encouraged. That's where my actual field is. Go ahead.
When you parallelize the Intel
I think we have a microphone coming.
When you parallelized the Intel compiler, can you give an idea of the speedups that you actually got?
Yeah, that was that one slide. Let's go back and take a look. Probably wasn't real clear.
I wasn't.
Yeah, no problem.
Paying attention.
I mean, it's like I say, it's a little unclear what's actually going on here. But we measured the speed up on a set of spec mark programs, and then so we had the series. We then measured them on different platforms, different configuration of systems, where these represented a threading model where we didn't try to balance the workload across all the threads. We just threw all the work on some threads. Here we're trying to balance the loading of the threads. So that B versus U is balanced versus unbalanced. And so I guess, I sort of feel like, well, the best case is balance 16, but maybe today that's probably okay. But, perhaps 8 CPUs is a more generic mainstream system today in most developers, most production build situations. And so we're seeing about sort of a 2.5 times increase on an 8-way system, 8 CPU system. That was the question? Yeah.
Yep.
Okay.
Thank you.
Yes.
My question is also with regards to that case study. You mentioned that originally you'd had nearly 3,000 errors, and so they had to go through and prune through them. My question, first of all, was what was the general categorization of those errors? Were there any sort of any useful lessons that were brought out of that? And then secondly, you'd mentioned in passing that you had some automatic tools for making changes to code to identify some problems. Can you talk more about those?
Yeah, I didn't. So the second question first. I didn't go into that in great detail. The people on this project had the advantage of being able to know sort of the internal data structures and being able to write custom tools on their own to focus specifically on the problems they were seeing. So that was part of what they were talking about. This was a sort of a prototyping project, so they had a little more leeway than perhaps a end user that does not work at Intel might have relative to the kinds of automating they could do. And I didn't go into that because I wasn't sure that was relevant in the time I had to talk. First one was, were there any, say again the first question?
Were there any useful classifications of errors they saw? So there's anything to look into in more detail.
I guess I could invent an answer to standing up here, but I guess the answer is I don't know exactly. I'm trying to remember. I'm sure there were, but I don't think I could regurgitate them right now. Sure. Other questions? Yes.
I was interested in knowing what the comparison of this performance number was compared to the like parallel make, like file level parallel make. I'm sure it didn't give as much boost compared to that, but if there was anything done to figure out.
This is a good question, and actually, I needed to be clear about the fact that this was kind of a research project, not a real world thing. And in fact, we have the compiler that we ship today is not the parallel version. We still ship the serial version because parallel makes do a fine enough job. This was an experiment just in taking a 1,000 source file program and seeing what you could really do with it. Okay. Yes. The microphone guys are a little lazy here. It's summer in Berkeley. I mean, Okay.
Are there any data races that the inspector can't detect?
Any data races that the inspector can't detect? There are some bizarre boundary conditions. I'm not sure I can cite them off the top of my head. We've got a guy, Matt Frank. I don't know if you know, PhD from MIT that was a professor at Champaign-Urbana and is now the lead architect on this project. So I had some discussions with him, and he can point out certain kinds of condition variables, I think, where there's some issues with trying to detect these well. But they're, in the real world, I think they're relatively rare. And I think it's still a benefit to go through this, even if there's, a 10 to the minus 5% kind of a issue with finding everything. Okay? So we have a minute left. Okay, well, I'll hang around for a minute. Again, especially my field tends to be performance, so we had some questions about cache misses and bandwidth measurements from the previous session. So if you have anything you'd like to ask, let me know, and I can probably give some more formal answers in the material that we post. So thanks a lot.